Alright, so I will say here, while I'm getting set up, the next chapter is directly is the building is on building a graded algebra from a filter in an algebra, and that is just exactly what we have already seen from Sarah. So we're going to skip over that. It's, you're taking the plus grade to be the union of all grades above a grade. GR alpha for that grade alpha be that grade of the plus grade, and you're just direct summing them all up to get your graded group. And you can define it in algebraic structure. We've seen all that. So our first actual topic here is going to be central filtrations on a group. Central filtrations on a group. We're going to let G be a group. A real filtration of G alpha on G is called central. If G is the union of the positive grades and the commutator x comma y, which is, we recall is x, y, x inverse y inverse. They write it here like this. I think it doesn't matter. X, y of an element G of an element x in GA, and y is in GB. I guess alpha and beta are going to be their grades. Is in the grade of alpha plus beta. This translates in terms of our order function to our order being strictly positive and the order of the commutator of two elements being at least their sum. We then deduce that the order of a commutator is strictly greater than the order of an element if that element does not have grade of positive infinity. And the grade of the conjugate of x by y is just the grade of x. Thus, each subgroup G alpha is normal. So they form a fundamental system of neighborhoods of our identity for topology compatible with G as a group And for the rest of this chapter, we're going to assume that our group has a central filtration over G alpha. We're going to define the subgroup G positive alpha as the union of G alpha for G beta for beta greater than alpha. Typos are getting more numerous in this book as we go forward. With then G positive alpha being G alpha being G when alpha is non-positive. Then we have that the commutator of a subgroup or G alpha and a subgroup G beta lies within G alpha plus beta, of course. We also have that G alpha positive with G beta. We may have seen this all before, but it's good as review. Lies within G positive of alpha and beta. And the commutator of G and G alpha lies within G alpha plus. By this last one, formula G alpha positive is a normal subgroup of G alpha for all alpha, and the quotient group GR alpha of G defined as G alpha over G alpha plus is commutative. We are right. If you recall, yeah, the graded version of G is the sum of the direct sum, I guess I'll use this, of the GR alpha in G with the obvious graduation, real graduation. And then the alpha grade of G is 0 for non-positive grade. And they go over again that we can give this an algebra, a Lie algebra structure, in much the way we did before, so I guess this was mostly review. Now let's look at an example of a central filtration. Let A be a unital associative algebra with a unital algebra filtration of A alpha such that A0 is A. Then A alpha is a two-sided ideal of A for all real alphas. Let A star be the multiplicative group of invertible elements, of course, of invertible elements of A. For alpha in 0, we're going to let gamma of alpha be the set of elements in the multiplicative group of A such that x minus 1 is within the alpha grade of A. We write gamma as the union of all gamma alphas, and gamma beta be gamma for non-positive beta. This comes as a proposition that our gamma is a subgroup of A star, and gamma alpha a central filtration on gamma. And the proof: gamma is the union for alpha positive of gamma alpha by construction. And we get that each gamma alpha is the intersection of smaller gamma betas from A alpha being the intersection of smaller A betas. We show first off that alpha is a subgroup, gamma alpha is a subgroup of A star. One is clearly in gamma alpha. Then we let x and y be in gamma alpha. So x minus 1 and y minus 1 are in A alpha. As the alpha is a two-sided ideal of A, the formula first off xy minus 1 being equal to x minus 1 times y minus 1 plus x minus 1 plus y minus 1, and the formula of x inverse minus 1 being equal to negative x inverse of x minus 1. These imply that x, y minus 1 are in A alpha, and that x inverse minus 1 are in A alpha. So xy is in gamma alpha, and x inverse is in gamma alpha. As if you recall, gamma is the union of positive gamma alphas. Gamma is a subgroup of A star. Now, we want to show its essential filtration. So alpha be positive, beta be positive, and x be in gamma alpha, y be in gamma beta. And we're going to let c be x minus 1 and eta be y minus 1. Then the commutator of x and y minus 1 is equal to x inverse y inverse times the Lie bracket of c and eta. So you know that c is in alpha A and eta is in alpha B. So xc alpha minus alpha xc is in alpha A plus B, which is a two-sided ideal. Of A. Thus, the commutator xy minus 1 lies within A of alpha plus beta. So the commutator of x and y is also in gamma of alpha plus beta. Alright, now, remark. Let alpha and beta be non-negative, x be in gamma alpha, y be in gamma beta. Then, first off, x inverse minus 1 is congruent to negative x minus 1 mod a to alpha xy minus 1 is congruent to x minus 1 plus y minus 1 mod a of alpha plus beta. And then the commutator of x and y minus 1 is congruent to the Lie bracket of x minus 1 and y minus 1 mod a alpha plus beta plus the infimum of alpha and beta. We've already seen the first two. Let's look at the third one. If we have c is x minus 1 and eta is y minus 1, then we know that from before that the commutator of x and y minus 1 minus the bracket of c and eta. I should write this on a new line actually. The commutator of x and y minus 1 minus the Lie bracket of c and eta gives, all this is going to be multiplied by something, so the inverse of x minus 1 plus the inverse of y minus 1 plus the product of x inverse minus 1 and y inverse minus 1 multiplied by the bracket of c and eta as the bracket of c and eta are in alpha a of alpha plus beta, c inverse minus 1 is in a alpha, y inverse minus 1 is in a beta. We are done. Now let G be a group. Don't know why I did the period there. rho a homomorphism from G into R gamma. For all real alpha, we write that G alpha is equal to rho inverse of gamma alpha. And as these gamma alpha is a central filtration, on gamma, the collection of G alpha is a central filtration on G. Proposition: for all real alpha, there exists a unique group homomorphism G alpha from GR alpha of G into GR alpha of A, which maps the class modulo G alpha positive of some element A inside G alpha to the class modulo A alpha positive of rho of alpha minus 1. Part 2. Let G be the group homomorphism of G of the grade of G into the grade of A, such that the restriction of G to the alpha grade of G is G alpha for all alpha. Then G is an injective homomorphism of Lie integer algebras. Proof: for part 1, let alpha be positive. Then we know that we know by hypothesis for all A in G alpha, rho of A minus 1 is inside the alpha grade of A. Let P alpha of A denote the class of rho A minus 1 modulo A alpha positive, as A of 2 alpha lies within A alpha positive. We see that rho alpha of AB is rho alpha of A plus rho alpha of B. And A is in G alpha positive if and only if rho of A minus 1 lies within A alpha positive. So G alpha positive is the kernel of P alpha, which sends G alpha into the alpha grade of G, GR alpha of A, I should say. So then by quotient, PA defines, where's my button? An injective homomorphism G alpha of grade alpha of G into grade alpha of A. We also note that for alpha non-positive, GR alpha of G is 0, and so G alpha is itself 0. For part 2, as G alpha is injective all real alpha, G is injective. We show that G is a Lie algebra homomorphism. As the alpha grade of G is 0 for alpha is negative, we are done by P of alpha plus beta of the commutator of A and B being the Lie bracket of the commutator of P alpha on A and P beta of B. Alright. And looks like we'll be finishing off this chapter today with integral central filtrations, which I think we have already mostly seen. The problem, I should have filtered this out more ahead of time. I'll go through roughly what this is, but this is, I think, mostly going to be familiar stuff. So I might skip over, just read out loud a lot of it. Integral central filtrations. I don't want to go over it under time, but I don't want to go into the next chapter either. So recall that a filtration G alpha on G is integral if G alpha is equal to G of the ceiling of alpha. Which is equivalent to saying we have a sequence of subgroups, say Gn of G, such that over integers n, where G1 is G, each Gn lies within Gn plus 1, we've seen this before, and the commutator of Gm and Gn lies within Gm plus n. Then for positive n, and at least 1, we have that Gn is a normal subgroup of G, and that the nth grade of this as Gn over Gn plus 1 is commutative. on quotients by quotient, the map, the mapping of x and y as an ordered pair to x and y as a commutator, which I'll write down the formula for. So this is gm times gn going into gm plus n, defines, from this we can define a graded Lie algebra structure of type n, of natural type, over the ring of integers. They show here that the lower central series is an integral central filtration of G, which we have already done. There's one more fact here they have here, which we probably already did, but I kind of want to go over again just for the sake of going over it again. Maybe just for the sake of padding out this video, if nothing else, a little longer. Which is that the graded version of G is generated by GR1 of G, which is equal to G over its derived algebra. Or derived group, I guess, because G is a group for, I'll write that out here, group G. So this is not a derived algebra, it's, I guess you call it a derived group, maybe. I don't remember if that's an official name or not, but it's what I'm going to call it. So we're going to let L be the Lie subalgebra of the graded algebra of G generated by GR1 of G. We will show that L lies within the nth grade of G by induction on N. Of course, it's true by definition for n equals 1. So we're going to let n be greater than 1, and let L contain the n minus 1th grade of G. As the nth lower central series of G is the commutator subgroup of G with the n minus 1th lower central series element term of G. We see by how we have defined the Lie bracket, the Lie algebra, we see that the nth grade of G is the quotient of the first grade of G and the n minus 1th grade of G, which has to lie with an L. And this shows, that's our proof, and this shows that the nth term in the lower central series of the grade of G, and I realize why I was put off by that, is because they formatted the lower central series differently for like 3 lines for some reason. The nth lower central series of the graded version of G is the sum for n, at least n, of GRM of G. And remark, like I said, just yeah, I think we'll go for this remark just for the sake of getting our video time a little longer. Remark, let K be a ring, N a positive integer, and A the set of lower triangular matrices in as a n by n matrix on K. For non-negative P, let AP be the set of xij of matrices xij in A such that xij is 0 for I minus j being less than P. Then A0 is our A, and the product of an element in AP and an element in AQ is the product of an element in A of P plus Q. We're going to let gamma P be 1 plus AP. Then gamma 1 is a subgroup of the general linear Lie group of n dimensions on K called the strict lower triangular group of order n over K. We see that gamma P is an integral filtration on gamma 1, and we also see that as the nth grade of gamma is just the identity matrix. We see that the group of gamma 1 is nilpotent. That's the end of this whole chapter. I guess we're not really doing little chapters, we're doing sections. Up next is Magnus algebras, which I don't know about. I'm kind of scared of, but I don't know how far in this book of Bourbaki we are. That would be nice. I'll check that before next time, but I think we'll just carry on with Bourbaki for a little longer. Because right now I want to get all the books done up to... Our goal is to get all the content of all the books before Lie group's done. So there's some Bourbaki left to do. And I don't think Humphreys covers Lie groups at all, so I want to complete all of Humphreys, and so maybe I'll finish Bourbaki before the Lie group, depending on how much there is, and then complete Humphreys, and then we'll flip between Sayre and Bourbaki for Lie groups. Although my professor said that the text on Lie groups isn't as good. So maybe I'll, in the end, when we get to Lie groups, we'll see when we get there. But yeah, we still have a ways to go before then anyways. So yeah. Thanks for watching, I guess.